Now that we've looked at a few examples on factoring higher degree polynomials, we'll then bring this into equations where we have to use the factoring skills to help solve the equations. Now, keep in mind that the degree of the higher degree polynomial function is also the number of solutions to the equation. So whenever we see example 3, we have 2x to the 5th. That's the highest exponent value in this equation, and we know that we should come out with 5 possible answers. Now, you can see in the first step that the very first thing you want to do is move the 14x to the 3rd over to the left side and write that in standard form. And then we would go about factoring in the new ways that we've learned how to factor. And then ultimately, we're going to use the zero product property in the final step to help solve for x from each factor. So a lot of that should look very familiar to you, and we're just applying some new factoring skills. So let's take a look at this next example. Sample problem number 3. So go ahead and try this on your own, and then come back and take a look at the solution. All right. Now, since this is an equation, one of the advantages that we have is we have 2x to the 5th minus 18x, and 2 is a common monomial between those two parts. However, we don't need to just factor out the 2. We could actually get rid of it through division. So I'm going to do that here. I'm actually going to divide everything by 2 and just eliminate it completely. So I'm going to have x to the 5th minus 9x equals to 0. And that's a much simpler equation to work with. Now we can see that x is a common monomial, so I take that out, leaving me x to the 4th minus 9. As we said in the previous video, you should always be looking for a second level or a second layer of factoring. And you can see here x to the 4th minus 9 is a perfect square on both parts. So this is a difference of squares. So we're going to factor this one more time. That's going to give me x squared plus 3, x squared minus 3, and don't forget about your equals to 0. Again, we would look for more factoring, but x squared plus 3 and x squared minus 3 cannot be factored. So now that we have 3 parts here, we can separate it using zero product property. So we can say that x equals to 0, x squared plus 3 equals to 0, x squared minus 3 equals to 0. And now you would solve these 2 remaining quadratics just as you did in the prior unit. Okay, so now what you can see here is we have 1 solution, 2 solutions, and 2 solutions for a total of 5 solutions. So that means we got all of the roots out of this equation. All right, so that's a good example of how you can use these factoring skills to help solve equations, higher degree polynomial equations. If you recall from the quadratics unit, we showed you a substitution method that you could use to factor more complex quadratic equations. And this is where we used a u to represent any expression that was repeating somewhere within the expression or the equation. And so this is the same thing here that we're doing. We're using a u in place of a more complex expression. You can see in example number 4, we just simply replaced the w squared just to make this a simple quadratic and make the factoring much easier. The one thing that you want to be sure to remember is to always go back and replace the u with the original expression, and always look for further factoring in problems like this. So let's take a quick look at sample problem number 4. If you go ahead and take a look at that and then come back and watch the solution. So we can see here that u in this case is going to replace the expression x squared minus 3. And when doing that, we get a much easier quadratic expression to factor. Now, if you wanted to go to the trouble of foiling out all of that, combining like terms, and then trying to group this, you're more than welcome to do that. But I think this is a much more straightforward method. So we can factor this into u plus 3 and u plus 4. And now we can come back and we can replace the u in each part, and then finally we just need to consolidate the terms, and so -3 and +3 actually cancel each other out, and then we have just a +1, and so that's fully factored at that point. We'll take a look at another problem here. The next problem goes back to a factoring skill that you learned in quadratics as well. It's called grouping, and you can see we have a cubic here, but it's not a trinomial and it's not a binomial, so we have to go another route. So anytime you see a 4-term polynomial, probably the first thing that should come to mind is a grouping method. So I'm just going to start right from the beginning, grouping those off, and you can see that the x plus 1 term is common between this first term and the second term, so I'm going to factor out an x plus 1, and in the process x squared plus 3 is going to be remaining. Again, x squared plus 3 cannot be factored, but always be on the lookout for if that could be factored. Okay, so now you've seen us take from the quadratics unit some more factoring skills and applying them here. For this last video in this lesson, we need to discuss a potential issue that could pop up quite frequently when factoring higher degree polynomials and then solving higher degree polynomial equations. If you recall from the quadratics unit, we had a special case where we had perfect squared trinomials, and if you recall, in a perfect squared trinomial, we touched the x-axis exactly once, thus leaving us one real solution, even though we knew that the quadratic equation should give us 2 solutions. We called this situation a multiplicity. So if a root happens to occur more than once, we can say that it has multiplicity. In the case of the perfect squared trinomial, the x minus 5 occurs twice in the given example here, and so we can say that 5 is a root with a multiplicity of 2. So we can see this happen quite a bit, especially when we have cubics and then 4th degree, 5th degree, 6th degree polynomials, however high you want to go up with that. So you can see in sample problem number 6, we're going to try to figure out how to solve this and find all of the real and imaginary solutions, and then decide which roots have given multiplicity. So you can see that the degree is 5, and we're just going to try to find all 5 of them. So I'm just going to walk through this one with you real quick. So the first thing I'm going to do is something that I did earlier. I'm going to use the equation to my advantage, and having that equal to 0 is good because it's still going to end up equaling to 0 when it's all said and done. So we have x to the 5th plus 4x to the 3rd equals 0. So you can see we're going to factor out a common x to the 3rd, so that's going to leave us an x squared plus 4 equals to 0. Now, x squared plus 4 is not factorable, and so we can go ahead and break this up with zero product property right now. So I'm going to get x to the 3rd equals 0, and I'm going to get x squared plus 4 equals 0. Now, you haven't done a lot of roots other than the square root, so this may look a little new to you, but this should be very comfortable as we go forward. If we have a x to the 3rd, we can eliminate that 3rd power with a 3rd root, and of course we have to do that to both sides. So that's going to leave us just x, and that's going to leave us equals to 0. Now, here's the thing. We know that x to the 3rd should have left us 3 solutions. So in this particular case, that's going to have a multiplicity of 3. So this solution has a multiplicity of 3. And then we can also solve the other one. And you can see here that we have 2 solutions here, and we have 3 solutions there because of the multiplicity. So we have all 5 solutions as a result. And so this is something that you're going to run into occasionally later in the unit when we start discussing graphing. Discuss crosses the x-axis versus just when it touches the x-axis, and how that has implications in regards to the multiplicity. Alright, that's a good little introduction to that concept that we'll be using a lot more later on.